Hello everyone, I'm Tianyu, and today I'll be presenting our work on supporting fast transactional workloads on universal columnar data file formats. Before we get into the paper, meet Joy, a data scientist starting at CMU. Joy wants to do some analytics on his application data from an OLTP system. He is also not known for his patience. Now, how would Joy go about doing this? In an ideal world, an omnipotent database sits at the center of the universe. Applications issue transactions to the DBMS. Joy asks his questions to a DBMS on SQL. His questions get answered. Everyone is happy. Joy is not convinced, though. Hear that there's this thing called Python, and every data scientist uses it. Any chance you guys can support Python? Well, that's easy enough, right? Just take the data out of the DBMS and do whatever you want with it in your Python tool. There's just one problem here. The bandwidth from a DBMS to an external tool is very low, as you can see from this very thin arrow here. Our current protocols are really designed to send small answers, not load large corpus of data elsewhere. Overall, we get terrible data transfer rate with this approach. So what do we do? In practice, many organizations have to separate their data storage into a dedicated OLTP frontend that processes transactions and periodically prepare the data for downstream analytics, like this. This process is usually called extract, transform, and load, or ETL. This backend data warehouse can then much more efficiently interface with analytical tools and get answers to Joy. Did we say Joy is not patient? Well, Joy is currently not very happy because we must wait until the next time the two systems synchronize before he can look at the latest data. He wants those answers now, not tomorrow. The reason for this delay is that OLTP systems and OLAP systems traditionally have different formats, each optimized for their own needs. Transforming between the two is necessary. The answer to Joy's request then boils down to a key research question. Can you efficiently run both transactions and analytics on one storage format? If you can, then maybe Joy doesn't have to wait until tomorrow after all. Let's think about that for a bit more. This idea of a universal format is not new. Plenty of analytical tools do have standardized data formats, such as Apache Parquet or Apache Arrow. There's half our solution to the universal storage format question right there. The half that remains is whether we can run OLTP workloads efficiently on those formats. The answer to that question turns out to be a yes, and that's what I'm going to talk about today. For the remainder of today's talk, we'll first look at one such universal analytical format, Apache Arrow. We'll then discuss in detail our technique for running transactions on Arrow. And lastly, we'll show how having an Arrow-compatible OLTP system can bring some exciting opportunities across the data processing pipeline. To start, let's look at the Apache Arrow project. Arrow is a cross-language development format for in-memory columnar data. That is, at its core, Arrow has a standardized language-agnostic representation of structured data. This is an interesting format because it is widely used, and often is an interface between systems. For example, if one is to export data from pandas into TensorFlow, they can eventually do so using Arrow. Let's take a more detailed look at the Arrow format. Suppose we have a table like this, with one ID column of integers and one name column of strings. Arrow first uses a metadata header to encode the schema like this. Of the two columns, the integer column is considered a primitive, and we can just represent it with a contiguous buffer of 4 byte integers like this. The string column is represented as a buffer of characters and an array of offsets like this. This is a very efficient representation if you're scanning through a table. However, there are two major problems with it if you're to modify the data. Deletion and varlen updates can both cause the program to change all event tuples, in the worst case, to maintain the Arrow invariant of contiguous data in memory. By now we can see that the key challenge to running transactions on an analytical format like Arrow is write amplification, and any solution will need to somehow alleviate this cost. Our solution relies on a key assumption in OLTP workloads, that most of the writes happen to a small hot portion of the database, and the hot data cools down to become more read-heavy over time. This allows us to keep Arrow data in a write-efficient representation when it is hot. As the data cools down, we can transform it into the read-optimized Arrow format. Let's first look at our relaxed Arrow format for transactions. On the right, you can see the read-optimized table from before. These are the Arrow buffers readers expect, and we cannot make much modifications to it. Therefore, we instead allocate these two new columns for transactional information. The first one is a bit vector of whether a tuple is present, used for deletion. For variable length updates, we allocate 16 bytes for each row, 4 bytes of size information, 4 bytes of prefix, and an 8-byte physical pointer to the varlen value in memory. With these new columns, we can absorb writes and avoid updating the underlying arrow storage. We give examples here where we mark deletion with the present bitmap and update virulent values by pointing to out-of-line new buffers. To get a fully functional transactional engine out of this idea, we allocate one last extra column for use as a version vector. This holds a physical pointer to the start of a version chain. Our system uses newest to oldest version chaining, where every entry is a delta. We can then use the tried and true multi-version OCC protocol to implement transactions. A transactional workload would add a delta to the version chain and then modify values in place. For deletes and virulent updates, this goes to transactional columns, but for fixed length values, we allow transactions to directly update values within the arrow buffers. Let's see where this gets us. On the left, we have the hot portion of the database. Some of the data is in arrow, but much information is scattered in version deltas and transactional columns. On the right-hand side, we have the code portion of the database. These tuples are not being updated, and all information is in arrow. Readers can directly scan through the arrow buffers to obtain information. As we have mentioned before, we're going to go from left to right through GC and compaction. This is where we reconstruct arrow columns using information in the transactional columns. The other direction, meanwhile, requires no transformation. Writers just need to make sure they're not interrupting concurrent readers. This is by no means an exhaustive presentation of the technical challenges involved in our solution. Ensuring that the whole pipeline is thread safe without introducing new bottlenecks for transaction is tricky. We cover this topic much more in detail in the paper. In fact, we're able to generalize some of our techniques into a standalone framework to safely perform background maintenance with active transactions in an OLTP system. Please check out both papers if you're interested in the details. We will now show some of our results. We implemented our scheme in CMU's noise page system and ran the tried and true TPCC benchmark on it. All transactions execute as stored procedures, and we report overall transaction throughput. We can see that noise page loses just below 10% performance when we turn on this transformation feature, proving that our transformation is lightweight. In realistic scenarios where transactions are coming in through the network, this overhead is often negligible. Cool, all this transaction talk is fun and exciting, but what does this have anything to do with our friend Joy here? Well, for starters, let's go back to our original use case, where Joy wants to do a select star over his OLTP system. With noise page, the vast majority of OLTP data is already available in a format understandable by Python. So we can skip the whole wire protocol and query thing and just dump raw bytes onto the wire for Joy. For the small hot portion, we'll have to transactionally materialize a snapshot and send it to Joy, but that hopefully won't be as expensive since the amount of hot data will be small. We ran an experiment for this use case, loading about 7 gigabytes worth of TPCC data directly into pandas. For this experiment, we marked 80% of the database as cold and fully transformed. For the code portion of the database, there are a couple of things we can do here. One, we can leverage the Arrow ecosystem and use their zero-copy RPC library to send the data. Or two, because we're just doing raw byte copy, use RDMA to quickly send the data. We compare these against two baselines. One is sending data over the Postgres wire protocol, and the other to send it with an improved wire protocol proposed by this paper. We implement both protocols on top of noise page according to their specification. Here's what we get with Arrow storage. Noise page is able to almost saturate the 10 gigabit network we tested it on. Arrow Flat in particular is surprisingly able to achieve performance close to RDMA thanks to Arrow native storage. The two wire protocols, on the other hand, are not doing so well. This is just a small example of what universal storage can do for us in the data processing pipeline. Looking ahead, we can try to add more functionality to noise page's transformation process and introduce features such as filtering or aggregation, essentially pushing the entire ETL pipeline, including some stateful processing, up into the OLTP system. Or, perhaps more interestingly, because noise page has Arrow data natively, Arrow can serve as an API between the database and external tools. Because much of the data science world is programmed to work with Arrow, in theory, any of them can execute directly as UDF on noise page, because noise page's data is mostly in the same format. This opens up some exciting opportunities for compute shipping architectures in addition to the data shipping ones, like the ones we showed before. To summarize, we believe it is critical for DBMS engineers to design for performance gain across the data processing pipeline. Hopefully, I've convinced you all today that a format like Apache Arrow can support efficient OLTP with a couple of tricks. And we believe that if you're building a new DBMS in 2021, there's no reason for you to invent a new format. Use a universal format. It is doable and brings many exciting opportunities from across the pipeline.